All right, awesome. Recording has started. So again, just as a reminder, once we're done for today and I get the video processed and uploaded, I'll stick it right here in the Electron shells Zoom meeting recording section. And if you ever want to go back and look at the notes for today, they're going to be right under the items section in the 9/16 Wednesday notes right here. So I apologize for not getting these posted sooner. I thought for sure that I had them posted late yesterday or early this morning until I looked about a couple hours ago and was like, oh, gosh dang it, they're still not posted yet. So hopefully, I think only a couple people tried to do the homework before being like, what the heck is this going on? So hopefully, if they did do the homework, they'll be able to go back and kind of fix some of the stuff, because I have no idea how you know what was going on without looking through these notes. So apologies for me again. In the future, I'm going to try to be a lot better about posting the notes as soon as they're ready, even if it's like a couple days in advance. That way you can look at them if you want to, and you'll have them ready for when the assignment for that day posts. So these are our electron shells and reactivity notes. So that's what we're going to be talking about for IPC today. Alrighty. Make sure we got the right thing going here. I'm always scared when I like start one of these presentations because sometimes Zoom is weird and it'll just not show what you think it's showing. And so I always try to take a second to double check and make sure that you guys are seeing what I'm seeing. But it looks like you are, and that is all well and good. So electron shells and reactivity. So if you remember from yesterday, electrons are our negatively charged little particles that don't get to hang out in the nucleus of the atom, right? The electrons don't go in the middle with the protons and neutrons. The electrons go around the outside of the atom. So they have to go kind of in these shells or orbitals that we're going to be talking about in just a second. So if you remember, yesterday we were all about the number of electrons, how many electrons are in each one of these atoms. And we talked about how if you can figure out the proton number, which you can do just by looking at the atomic number on the periodic table, once you get the protons down, then balanced with the number of electrons. And so that's how we were able to determine our electron numbers from yesterday. We just looked at the protons and said, if that's how many protons that we have, then we have to have an equal number of electrons. So they all balance each other out. The positives and the negatives are all balanced. So in a super simple atom like hydrogen, hydrogen only has one proton, so it has one electron. The plus and the minus balance each other out. So we talked about numbers yesterday, but what we did not talk about is where do all those electrons go? So we know that the neutrons and the protons are hanging out in our nucleus down here, right? And then the electrons, we kind of said they're just around the outside, they're going around. But they just don't float randomly around the atom. Right? They're not like a balloon in the breeze, just kind of floating around wherever they want to go outside of that atom. Instead, they get organized into a specific set of structures. And so that's really what we're going to be focusing on today and what your homework for tonight is going to be about. So instead of just randomly floating around, instead, electrons orbit atoms in shells. So if you think of the nucleus of the atom being the center point, a shell is kind of like an invisible layer of electrons that gradually spreads out further and further from an atom. And each electron shell can only hold a certain number of electrons on it. So electrons can have lots and lots, or excuse me, atoms can have lots and lots of electron shells around them. But in this class, we're just going to focus on the first 3 shells. So if you want to kind of think about them as these rings around the atoms, we're just going to be focusing on the first 3 shells, or the first 3 rings. So the first shell that goes around that the atoms or the electrons are on can only fit 2 electrons. So hydrogen, like we were just talking about a second ago, he has 1 electron. So that goes on this first shell here. And then helium, he's got 2 electrons. He's the very next atom on the periodic table. He's got 2 electrons. So helium fills up his first shell right here. So once those 2 electrons are on that first shell, it is full. No more electrons can fit on the first shell. So if there's still electrons to go, if we still have electrons left over, they have to start filling in the second shell. So hydrogen and helium are the first 2 atoms on the periodic table. Lithium is atom number 3. And so since he's atom number 3, that means that his atomic number is 3, which means he has 3 protons, which means he has 3 electrons. And so we start adding electrons around lithium. We put 1 and 2 on that first shell, but now that first shell is all full. Lithium has a full first shell. So our third electron can't go on the first shell. He has got to start filling in the second shell. So lithium has 3 electrons, 2 on the first shell, but then that gets, and so 1 electron goes on our third shell. So that's kind of the basic gist of how these shells work, is we figure out how many electrons we have, and then we add to each shell until it gets full. And when that shell gets full, we move on to the next shell, the more outer shell. So let's skip a couple atoms ahead to carbon. So lithium is atom number 3. Carbon is atom number 6. So we used him for an example at the end of class on Monday, right? Carbon has an atomic number of 6, which means that carbon has 6 protons and 6 electrons. So because it has 6 protons and 6 electrons, that means that we have to fit 6 electrons on our electron shells. So we start adding to the first shell. We add 1 electron, we add 2 electrons. Actually, hold on, I just thought of a better way to do this. I forget that I have fancy zoom tools so I can draw on things. All right, so hydrogen has 1 electron. Ooh, I don't like that at all. Helium has 1, 2 electrons. Lithium has 1, 2, 3 electrons. And then we said carbon has 6 electrons. And so we fill in that first shell. We take electron 1 and electron 2. But now that first shell is full. So we can start filling in our second shell. We put electron 3 on the second shell. We put electron 4 on the second shell. We put electron 5 on the second shell. And we put electron 6 on the second shell. So we have 6 electrons total. There is 2 on the first shell and 4. Oops, that's not where that's supposed to go. 4 on the second shell. Right, so we start by filling in that first shell, but he can only fit 2 electrons. So then we start filling in the second shell, and we use up the remaining 4 to go on the second shell, and that gives us 6 total electrons that carbon has. What about if we jumped all the way to the end of that row on the periodic table over to neon? So neon has an atomic number of 10. So if neon has an atomic number of 10, how many protons are in neon? Anybody that wants to answer out loud or in the chat, how many protons are in neon? Anybody?
10. Is it 10?
10, exactly. Thank you, Melissa. And Alejandra got that too, 10, perfect, Alejandra. So neon has 10 protons. And so if neon has 10 protons, then how many electrons does neon have?
5.
No.
No. 10.
Exactly, there you go, Rebby. Neon has 10 electrons. Yep, Alejandra got it again. So remember, protons and neutrons are always going to equal each other. They're always going to be the same. So neon has an atomic number of 10, which means it has 10 protons, which means it has 10 electrons. So when we go to figure out how the electrons get arranged on those shells in neon, we take our first 2 electrons, 1 and 2, put them on that second shell, and then we still have some electrons left over, so we can add those, or put those on the first shell, excuse me, and then our leftover electrons can fit on the second shell. So we have 2 down here, and then electrons number 3, 4, 5, 6, 7, 8, 9, and 10 total. So we've got 2 electrons on our first shell, because then that's how many can fit. And we have 8 electrons on our second shell. So because of this, that means that neon has a totally full second shell, because our second shell can fit a lot more electrons than the first one, 4 times as more to be precise, but it still has a maximum of 8. So neon has a completely full first and second electron shell. No more electrons can fit on the second shell. So what if we go more than 10 electrons, right? There are a lot of atoms out there that have more than 10 electrons. Atoms like sodium, for example. Sodium has 11 electrons. So just like with neon and carbon and helium and hydrogen, we start adding our electrons the same way. So we've got 2 electrons on the first shell, but we still have some left over, right? And so then we can fit 8 more electrons on the second shell. But the 2 on the first shell and the 8 on the second shell gives us 10 electrons, but that's not enough. Neon has 11 electrons. So we need to put 1 electron on the third shell. So the third shell works very similar to the second shell. It can also only fit 8 electrons on that shell. So sodium doesn't quite have that many electrons. He's only got 11, so he only needs to fit 1 electron on that third shell. If we jump forward a little bit, silicon has an atomic number of 14. So silicon has 14 electrons. So if we fill in the electron shells of silicon, we've got our 2 on the first shell, right? We still have electrons left over. We've got a full set of 8 on the second shell, but we still have electrons left over. So after the first 2 shells, we've only put 10 electrons down. So we can fit 4 electrons on that third electron shell. So because silicon has 14 total electrons, it needs to put 4 on that third shell before it's got all its electrons spaced out. So we put the 2 on the first shell, that's 2 electrons down. We put the 8 on the second shell, that's a total of 10 electrons down. And then we still have 4 electrons left after that. And so we put those 4 electrons on that third shell. If we want to see an atom where our third shell is completely full up, we can look over at argon. So argon has an atomic number of 18, which, as we just talked about with neon, means that not only does it have 18 protons, but it also has 18 electrons. So argon has a completely full first, second, and third shell, right? Because we've got 2 electrons on the first shell, but then that gets full, so I have to move to the second shell. We can put our 8 electrons on our second shell. Now we've put 10 down, but argon has 18 electrons, so we still have 8 to go. We can put those 8 on the third shell of argon, and now we have a completely full first, second, and third electron shell. So whenever you're looking at the electrons of an atom and you're trying to figure out which shell would they go on or how many of them should be on each shell, all you do is add electrons to a shell until it's full, and then move up a size to the next shell, keep adding electrons and repeating that process until you run out of electrons. So obviously there are much bigger elements than argon. Argon's only number 18, but the periodic table goes up to 112, some such. But we're not really going to worry about the 4th and 5th shells and what all that means. We're just going to focus on atoms that have their first 3 shells and kind of talk about what that means for their electrons. All right, we're going to do some more practice with this in a second, but I know that figuring out all of these different shells and numbers can be a little bit tricky. So who has any questions so far? If you're not super sure about something or you want me to go over it again, now is the time to speak up.
So as of right now, we're only dealing with 3 shells.
Yep, exactly.
You're just kind of all over the place with that blue pen, but I think I'm following you.
Yeah.
Why are they called
This
shells?
class, we're only going to worry about those 3 shells. We're not going to worry about any of the bigger ones.
Okay.
All right. Do you have a question, Crystal?
Why are they called shells again?
It's essentially just a way to think about the space that the electrons are taking up. So there's not like a physical shell surrounding the atom, right? There's not like an eggshell surrounding the atom like the yolk is the nucleus, right? Instead, scientists just observed that whenever they did studies of atoms, they always found 2 electrons that were really, really close to the nucleus of the atom. And then a little bit farther away from that was an area where 8 electrons would circle around. And then
Okay.
farther away from that was an area where 8 more electrons would circle around. So it's not like a physical like string or a shell that these electrons are sitting on. Instead, it's just a kind of specific area outside of the atom where the electrons are floating.
Okay.
So at first, when scientists were first looking and studying atoms, they thought that the electrons just kind of floated everywhere willy-nilly around the atom. But as they did more research, they found that they only floated in these kind of certain configurations, these certain areas.
Okay.
I like to call them shells. Some people refer to them as orbitals because it's kind of like they orbit the atom, like the moon or the space station orbits the Earth. So if you want to think about it that way, you can too. So shells or orbitals, whatever you want to use the name for it, it describes just kind of a general area that these very particular numbers of electrons will float around.
Okay.
All right, awesome. Great question. Any more questions about electrons and orbitals and shells? All right, if you're still a little bit confused, but you're not quite sure exactly what question to ask, I'm going to take you guys through a couple more examples so you can hopefully get a little bit better understanding of kind of how to piece all these parts together. All right, I got to get rid of. Still kind of a little new to the drawing thing. There we go. All right, so let's look at some more examples of how we can figure out electrons on their shells. So nitrogen is the 7th atom. Let's see, I like purple. Purple's a good color. Yeah. Nitrogen is atom number 7, so he's got 7 protons, which means he has 7 electrons as well. So again, to figure out how they fit on the shells, all we got to do is count. So first shell gets 1, 2 electrons. Now the first shell is all full, so we move out to the second shell, which will get 1, 2, 3, 4, 5 electrons. So actually, hold on, I'm gonna redo the numbering there. So we put atoms 1 and 2 on the first shell, but we need to get up to 7. So atoms 3, 4, 5, 6, and 7 will go on that second shell. So if we count up how many atoms are on each shell, we know that our first shell was full, which means that has to have 2 atoms on it. And then our second shell got the leftover atoms, numbers 3 through 7. So he's got a total of 5 atoms on it. So we have 7 atoms, or not, keep saying atoms, that's my bad. Electrons, excuse me. 7 electrons total in nitrogen. 2 of them will go on our first shell, and the remaining 5 go on our second shell, which gives us a total of 7.
So, Mr. Stanley, is it always going to be 2? Like, is that
I was just going to ask that too.
Always,
The first shell
yeah.
only always 2.
The first shell, so this guy, this first shell right here, he'll always have 2. That's the maximum number that can fit on that shell. I'm not 100% sure why. I'm sure it's due to very complicated physics stuff and quantum forces and whatnot. But all I need to know, and all you need to know, is that the first shell, once it gets 2 electrons, it's full. No more electrons can fit on the first shell after 2. So yes, the first shell will always have 2 electrons. The only time that it will not is for the very, very first atom in the periodic table, hydrogen, because hydrogen only has 1 electron. So he's just got the one little guy floating around outside him. But everybody else will have 2 on this first shell here. All right, good question. All right, so I think we already talked about this guy a little bit before, but I wanted to show it again because it provides a really good example. So neon has number 10 element, so he's got 10 electrons. So again, if we want to figure out how many are going to be on each cell, we start on our first shell. We've got 1, 2, just like we talked about, but we still have a lot of electrons left over. We need to count up to 10. So electrons 3, 4, 5, 6, 7, 8, 9, and 10 go on our second shell here. So that's 10 electrons total on our first and second shell. We've got 2 electrons on the first shell, just like there will always be. And we fill out the rest on the second shell, which is 8 that we still have to go. So the second shell has 8, and the 2 and the 8 together give us a total of 10 electrons. So neon has 10, 2 go on that first shell, and 8 go on the second shell. And the 2 and the 8 together gives us our 10 total that neon has. All right, let's go a little bit bigger than neon even with aluminum, number 13. So he has 13 electrons. So where are these electrons going to go on these shells? Let's count and find out. So aluminum, we got 1, 2 on the first shell, just like we have in the past. We still have electrons right over, right? 2 is a lot smaller than 13. So we keep counting. We have 1, 2, and then 3, 4, 5, 6. Man, drawing numbers on a computer is a lot harder than it might look. 6, 7, 8, 9, and 10. But now our second shell is full, right? We just put 8 more electrons on this second shell, right? 2 on the first and 8 on the second gives us 10. But 10, as you may realize, is still smaller than 13. we have 3 electrons left over. So those guys will go out on shell number 3. So 11, 12, and 13 go out on the 3rd shell. So if we were, how many are on each shell? Our first shell has 2, just like it always does. Our second shell got all full of electrons, which means he got stopped at 8, right? That's kind of his max, his cap. And then all the little leftover electrons ended up on the 3rd shell. And so we've got 3 electrons hanging out on our 3rd shell out here. So 2 and 8 and 3 together gives us 13 total electrons. 2 on the first shell, 8 on the second shell, and the remaining 3 on our outer 3rd shell. All right, we had some Alejandra, you definitely nailed it right there. 2, 8, and 3 on our electron shells. Excellent job. So that is how, at least the way that I like to use to figure out if I have a certain atom, how are the electrons arranged around its shells? So I like to start off by counting out the electrons on each shell. And then once I hit that shell's max, I just go up to the next shell and keep counting. All right. So now that we've done a couple more examples of the electrons on and their shells, does anybody have any further questions? Anything that they're still just not quite getting about how I got to the numbers that I did? Okay, I'm not hearing anything and nobody's put anything. Oh, there's a. All right. Carmen's asking a good question about the maximum numbers on shells. So yes, we already talked about how the first shell can only go up to 2 electrons on it. The second shell and the 3rd shell can only go up to 8. So that's why with aluminum, once we did our second shell and we put 8 electrons on there to give us a total of 10, we had to go up to the 3rd shell after that to put those last 3. So the maximum for the first shell is 2, and then the maximum for the second and 3rd shells are 8. There's not really a minimum number. I guess the minimum number for a shell to exist would be 1. So like Neon over here, right? He's got 2 on his first shell and 8 on his second shell. So he's completely full on both shells. He doesn't have a 3rd shell because he doesn't have any more electrons. There are no more electrons that we need to put anywhere outside of the second shell. And so if there are no electrons there, then we don't really consider that shell or that orbital being in existence. And so we only look at them when they have electrons on them. And again, we will only start putting electrons on a higher shell when the lower shell fills up, right? So with Neon, for example, he has 10 electrons. We would never put 2 on the first shell and then like 4 on the second shell and then 4 on the 3rd shell, right? That is not correct. That's not what happens. We have to fill up each smaller shell before we go to a bigger shell. It's kind of like if you put a small cup inside of a bucket and then start pouring water right in the middle. The cup will start filling up with water, but the bucket won't have any water in it until that cup starts to overflow and kind of start spilling the water out of it. So that's kind of what's going on here in neon and aluminum, or even in nitrogen, right? The smallest level, the first shell, gets filled up with 2. And once that happens, then we start filling up the second level. In neon, the second level gets filled up with 8, but we don't have any more electrons, so we don't have to go up to the third level. In aluminum, the first level gets filled up with 2, so then we have to move to the second one. The second one gets filled up with 8, and so only because it gets filled up with 8, then we move to the third shell and put those remaining 3 on there. All right, so hopefully that helped, Carmen. That was a good...
Oh, that's what we're gonna do.
Yeah, go ahead, Crystal.
That's what we're gonna be doing, like for the assignment. Like we have to draw it out like that. To get the
You
answer.
won't be, since it will be on the computer, you won't be drawing it, but instead I'll be asking you to write down.
No, like like on paper, like.
Yeah, you can write it down on paper if you want.
Yeah, to like write it
The
down.
assignment, I'm gonna have you write down like how many electrons will be on this shell based on this atom over here. Something kind of like that. So yeah, and I'll show you what the assignment looks like in a little bit once we kind of get through the notes. Good question though.
All right.
All right, anybody else have anything that they want to bring up before we move on from the electrons and the shells? All righty. So one thing that I want to kind of introduce now, because we'll start talking about it in more detail next week, is the idea that, so atoms, obviously there's tiny imperceptible particles. They can't really have wants or needs or desires. But the way that I like to think about it is that atoms are really happy, meaning like really stable, when their shells are full. So in my mind, it's almost like the atoms really, really like it. They're really, quote unquote, happy when they have full outer shells, whether or not that's a shell of 2 or a shell of 8. They really, really want their shells to be full. So what this means is that essentially the closer that they are to having a full shell, the more likely they will do some sort of reaction in order with another atom in order to share electrons or kind of distribute the electrons between them so that they can have a nice full shell. So an example of this would be like hydrogen. Hydrogen almost always exists in nature as H2 gas. There is almost never times when a single hydrogen atom is just floating around by himself with his 1 electron. Instead, 2 hydrogens will almost always immediately meet up and come together, share their 1 electron with each other, so that they can both seem like they have the full first shell, right? By sharing their electrons, it's almost like both of them have 2 electrons in their outer shell. So this is one way that atoms work together in order to kind of fill up their outer shells. Another way is that sometimes atoms will like donate their electron to other atoms that are looking for electrons. So like sodium is one of the examples that we talked about. He has 11 electrons. And so he has 2 on the inner, 8 on the second, and only 1 little lone electron on the third shell. Chlorine, on the other hand, has 17 electrons. So it has 7 electrons around its third shell. So sodium only has 1 electron. Chlorine has 1 electron missing on its third shell. So sodium will essentially give away its electron to chlorine. And then they'll kind of hang out really, really close to each other so that sodium feels like he has a full second shell with the 8 on his second shell. And chlorine feels like he has a full third shell by having that little 1 extra donated from the sodium. So this makes both of these atoms very stable and very happy because now they both feel like they have a full outer shell, which is what electrons and atoms really, really like. So we'll get into the details of exactly how this works and how electrons will share their atoms together in order to be kind of bonded with each other. But for today, the main reason that I brought this up, this idea of electrons kind of wanting to share their atoms wanting to share their electrons and filling out or emptying out those outer shells, is that this has to do with the concept of what's called reactivity. So reactivity is a chemical property of an element. So we talked about chemical properties last week when we were talking about how likely it is to do a specific type of reaction. And so reactivity of an element just describes how easily and how quickly a single atom will combine or react with other atoms or compounds, other molecules. So when atoms are very, very ready, very, very able to quickly and easily react with other atoms, that means that they have a high reactivity. If things are very difficult to react, it's hard to get them to react with other atoms, that means they have a very low reactivity. So elements that have a very empty outer shell, like sodium that we talked about earlier, right? His outer shell is very empty. He only has 1 electron on his outer shell. Or electrons that have a almost full outer shell, like chlorine over here. Chlorine's got a very full outer shell. It's only missing that 1 electron to make it a full 8 on the outside. This makes them more reactive because they're very, very easy. It's very, very easy for them to either donate their electron or take in a new electron and go through a chemical reaction that way. So for example, sodium is similar. Oh wait, no, this is sodium. Sodium has just the 1 electron on his outer shell. He has a very empty outer shell. And pure sodium is an extremely reactive metal. It's an extremely reactive element. This is not like the sodium that we talk about in your body when we're talking about salt. This is pure sodium that is not reacting or that has not combined with anything else. As soon as that pure sodium comes into contact with moisture in the air, with the water that's in the air, it'll like spontaneously light on fire and start giving off all of these kind of sparks and all of this gas because it's so reactive that it is very, very quickly chemically reacting with the air. And when things very, very quickly react, they tend to give off a lot of gas and a lot of light and heat. So more reactive just means that they're more likely to go through a chemical reaction. And the atoms that will do this are one that will do this kind of the most, either have a very empty or a very full outer electron shell. Whether or not that's the second shell or the third shell, they want their outer shell to be full. And so elements that have a very empty outer shell are trying to give those electrons away so that they can have a full second shell instead of an empty third shell. And then atoms that have an almost full second or third shell will react in order to try and bring in those extra electrons so they can fill out that shell. So the way that the periodic table is organized, the groups, which are the vertical columns, so our up and down columns on our periodic table, have very, very similar reactivity. All right, so group 1 is a very, very reactive group, right? There's sodium right there, and we just talked about how he's extremely reactive. So all the elements in group 1 are extremely reactive. On the flip side, all the elements in group 18 are extremely unreactive. These guys already have a completely full outer shell, right? We talked about neon a little bit earlier. He's got 10 electrons, 2 on the first shell and 8 on the second. So he's got a completely full second shell. These guys don't want to react with anybody else. They're totally happy as they are. They don't want to go through any sorts of reactions. Whereas these elements over here in group 1 are very, very reactive. They really, really want to go through a reaction so that they can get rid of that extra electron and have a nice full outer shell. So all the elements that are in a single column of the periodic table will be pretty similar to each other in terms of how reactive that they are with different types of elements. All right, then the last thing that I wanted to go over with you guys in these notes today is differences between the different major groups of atoms on the periodic table. So you've seen this periodic table a bunch as we've gone through some of these different notes. And you may have noticed that we have a big yellow section kind of in the middle, and then one little green guy over here, but a whole lot of green over on the far right, and then this kind of purple zigzag guy in the middle here. Those correspond to what type of element an atom is. And we can divide them into 3 major groups. The metals, which are the majority of atoms on the periodic table, especially on the left and middle section here. We have the nonmetals, which in this table are green and mostly make up the right-hand side of the table, with one little nonmetal hydrogen hanging out over here. And then our metalloids are this little in-between zigzag group of metals colored in purple on this table, because some of their properties are kind of similar to nonmetals and kind of similar to metals. And so the main thing that I wanted to do with these guys is just talk about some of the major characteristics of each one of these groups of elements. So metals are probably the easiest ones to think about because everybody has interacted with metal at some point in their life in some different way over the course of their life. So as most of you guys probably know, metals for the most part are shiny, right? You can polish them up and they have a nice gleam to them. They are pretty much all solids at room temperature. So room temperature is around like 72, 75 degrees Fahrenheit. And so the vast majority of metals out there will be solid formed when you put them at room temperature. There are some kind of cool exceptions, like if you've ever heard of mercury before. Mercury is one of the few metals that is liquid at room temperature. It makes this cool, shiny, liquid material when it's just sitting at the room temperature. It has a very, very, very low melting point. Metals are fairly malleable, meaning that if you take a big hunk of metal, you can through different processes, squish it down fairly easily into a flat sheet, a flat surface. So like aluminum foil, right? Aluminum is a metal. It's specifically just one atom on the periodic table. And so aluminum foil is just a whole bunch of aluminum that's been squished down into a thin sheet. Metals are also what is known as ductile, which means that we can pull and twist strands of metals and turn them into a wire. So a lot of the other types of elements on the periodic table will just shatter if you try to do any of this bending or twisting of them. But metals are pretty easily worked with, pretty ductile, and so they can be pulled out, stretched, twisted up, and not shatter on you on the spot. One extremely important aspect of metals for everyday living, for you and me, is that they have very, very high conductivity. So they can transfer heat or electricity from one area to another extremely quickly and efficiently. So this is why, right, you shouldn't be working with like a nobody has a plastic frying pan or a wooden frying pan, right? Because if you leave your wooden spoon in your boiling pasta water for for like a minute and then pick it up, the wood on the handle still is safe to touch, right? It doesn't get super hot because wood is a very bad conductor. On the other hand, if you left a metal spoon in your boiling pasta water, that would be extremely painful to pick up after just a couple seconds because the end of the spoon that's in the water is picking up all that heat and conducting it to the tip of the spoon that's out in the air. So this is why frying pans are metal, because they take the heat from your burner and transfer it very well across the surface of the frying pan into your food. This is why all of the telephone and electricity poles that are around your neighborhood are going into your house. All of the wires in there are metal. Like we talked about copper the other week, a very, very good conductor because electricity also flows over metals very well, right? If you stick a plastic fork or a wooden fork into your wall outlet, nothing's really going to happen. That material can't really carry that electric charge. Whereas if you stick a metal fork into your wall outlet, you're going to have a real bad time real quickly because the metal very efficiently conducts that electricity. So when you think about metals, think about like aluminum foil that I talked about earlier. It's shiny, it's solid at room temperature. You can squish it down flat, you can twist it up and turn it into a wire if you want, and it gets very hot very quickly and can move electricity very well. That's why you should not put aluminum foil into your microwave, because the microwave causes all the little electrons in the aluminum to get all excited and they start jumping out and sparking, and that's what causes microwaves to blow up. So that is metals. On the opposite end of the spectrum from that is the non-metals. So these guys have pretty much all of the opposite qualities of metals, right? They are not shiny. So if you do see one in solid form, it's gonna kind of look rocky or mineral-y. It's not gonna look shiny like a metal. They are mostly gases at room temperature. So things like oxygen, nitrogen, chlorine, helium, hydrogen. All of these guys are gases, and we think of them for the most part as gases. We have to get them really, 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 really cold in order to get them down into their liquid form. Nonmetals are very poor conductors, right? So sulfur is a nonmetal that does happen to be solid at room temperature, but sulfur is not going to be conducting a whole bunch of heat or electricity very well. And when they are solid, nonmetals are very brittle. So kind of think of them like rocks. You can't really squish down a rock flat into a single piece or sheet because it's just going to break on you, right? It's just going to shatter into like 500,000 tiny little pieces. So they have very brittle properties. You can't bend them, you can't twist them, you can't smush them down. They just shatter and break apart. So when you think of nonmetals, think of things like gases or rocks. They're not shiny. You can't use them for heat or electricity very well. If you try to bend them around, they'll break. And for the most part, most of the nonmetals are not things that you can interact with on a normal basis. They're gases that are floating around you in the air. So if we have our metals on one side of the spectrum and nonmetals on the other side, the metalloids fall in kind of a weird middle area. So they're called metalloids because they're kind of similar to metals, but not quite. So metalloids are solid at room temperature, like metals are, right? They make solid pieces. However, like nonmetals, they are brittle and hard. So it's very difficult to get metalloids to be formed into nice flat sheets or pulled out into wires. Most of them you can't really do that with. Metalloids can be conductors, but they're a specific type called semiconductors. So you may have heard a lot about semiconductors before. We use these a lot in computers and cell phones and things that have computer chips in them. And so essentially what it means is that they do conduct electricity, and when they do it very, very, very well, but they can only do it under certain conditions. So they have to be under certain temperature and moisture conditions in order to conduct electricity. Otherwise, it's not really going to work very well. So silicon is a very common metalloid that you guys may have heard about even if you didn't realize it. So silicon is found a lot in glass. So the little pieces of, or sand and glass, excuse me. So like the little pieces of sand, there's a lot of silicon in there. And then when we make glass, we usually make it out of silicon. Again, pretty brittle, right? If you break a piece of glass, it's going to shatter. It's not going to smush down into a piece. And silicon is also very important for these computer chips. So if you've ever heard people refer to Silicon Valley before, that's the area of California where a lot of major tech companies have their headquarters. So like Apple, Facebook, Google, they're all based in and around a specific area of California. And so because of that, people started referring to that area as Silicon Valley. So these guys are kind of like the weird hybrid of metals and nonmetals. They are solid like metals. They're brittle like nonmetals. They're sometimes conductors like metals, but it has to be under a very particular and very important set of circumstances. All right, so one final thing to kind of put together the two things that we were just talking about, the reactivity stuff and the metals and non-metal stuff. So like I mentioned, the atoms that are together in a column will tend to have similar reactivities. And in terms of the metals, the atoms that are more towards the left side of the periodic table have a higher reactivity, whereas the further you get towards the right, these guys over here have a fairly low reactivity. They're pretty low, unreactive for metals in this section. Nonmetals go the opposite direction. So nonmetals start as being fairly low reactivity. And then as you get closer to the right-hand side of the periodic table, you get higher and higher and higher, right? So carbon and nitrogen and phosphorus are fairly low reactive, but oxygen and especially stuff like fluorine and iodine are very, very highly reactive. But like I mentioned a little while ago, once you get to that final column, that group 18 over here, these guys go back to being extremely low reactivity because they've already got all the electrons they need. They don't want any more. So these guys are kind of just looking for electrons. These guys are super desperate to get electrons, but then these guys are good. They're all full. They don't want anything more. So a final note about some very important nonmetals. Carbon, atom number 6, is a super important element for living organisms. So you and me and your dogs and cats and the squirrels and the birds and nature around you, we're all mostly based on carbon. We use carbon for our energy. We use carbon to build a lot of the structures in our body. So carbon is an extremely important element for things that are living on Earth today. And then that final number 18 group that I was talking about a little bit ago that has that like almost no reactivity, they get the special name of the noble gases because I mentioned that they're super non-reactive. They have the full outer shells. So scientists, when they were coming up with this name, thought that these gases were kind of like thinking about like nobles or like snobby people, like, oh, they don't want to be associated with all of these lower nonmetals and gases over here. They can't even be bothered with those guys. So they're like the noble gases. They're too snooty, too fancy to go interact with any of those other lower class elements on the periodic table. So that's where they got their kind of funny name from over here. They're so unreactive and so unwilling to interact with the other elements on the table that scientists kind of thought of them as like these snotty noble gases. All right, and I believe that will bring us to the very end of our Wednesday notes. So does anybody have any questions about any of the stuff that we were just going over? Either the stuff on the reactivity or the differences between the metals, the nonmetals, and the metalloids kind of there in the middle. Anything that anybody is still a little bit uncertain about or wants a little bit more clarification on?
Yeah, just the shell part I want to go over again.
Yeah, sure thing.
Like what was I gonna say? How do you know like how many to put around there? Because you said the max was like 8, right?
Mm-hmm.
Okay, so when you're doing it, like for the lesson that you're just doing, so like again, when we're doing it, like for instance, I'm gonna draw it out because that helps me better.
Sure.
When I'm drawing it out, so it's just like 1, 2 in that first one, or like that's what I'm confused about. So you're just doing it like that?
Yep. And so that here, let me see. Can I? A pain. So yeah. So like if you're drawing it out here, let me. Let's create our own example here. So if we have like the example from earlier with aluminum, and aluminum is element 13. So he's got 13 electrons, right? So we've got our aluminum buddy, and we know that we're going to be putting electrons on some shells around him. So we start off with our first shell, and then we can put down electron number 1 and electron number 2. But now we've got a full shell, right? Our first shell, that guy can only fit 2 electrons on him. So now he's full, but we still have a lot of electrons to go, right? 2 is a lot lower than 13. So we've got to go up to our second shell to keep putting down electrons. So we got to go, we can put one more down. That's number 3. We can put number 2, a second one down, number 4. And a third one, and a fourth one, and a fifth one, and a sixth one, and a seventh one, and an eighth one, right? So now shell number 2 is all full, right? We've put 8 electrons down on the second shell. No more can go on there. But let's count up our electrons. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. We've only put 10 electrons down so far, but aluminum has 13 electrons. So what that means is that we still have a couple more that we need to put down. So we'll expand out to the third shell.
Okay, so now I get it. So that's what I was confused on a little bit. Yeah, I did get sidetracked. That's why I was like, wait, what? I missed it. But now that you're doing it like this, I get it a lot better. So that's what I was thinking. That's why I said, could we draw it out or whatever?
Mm-hmm. Right, exactly. So now we've put 2 on the first, 8 on the second, but that's only 10 electrons out of our 13. So we need to put 1, 2, 3 on the third shell, and now we've put 13 electrons down, which is the amount that aluminum has. We filled up our first shell of 2, we filled up our second shell of 8, and then we put the leftover electrons on our third shell. We only had 3 left over, and so we've got 3 electrons on aluminum's outer shell.
Okay, that helps out a lot. Thanks.
Yeah, sure, no problem. Anybody else have any other questions from the electron shells, the reactivity, or the metals and non-metal stuff from today? Alrighty. So before we finish up for today, I did want to show you guys the homework really quick. So it's a pretty simple assignment because I knew all this electron stuff is pretty new to y'all. So there's a little bit of some old stuff and a little bit of some new stuff all on one set. So for the assignment today, we're looking specifically at the atom oxygen. Oxygen is atom number 8. And so I want you guys to use this information that we got right here about oxygen to do a couple things. First, just like you did for the homework earlier in the week, I want you to figure out the proton number, the neutron number, and the electron number. But second, and more specific to the stuff that we did today, I want you to write down how many electrons go on the first shell of oxygen, how many electrons, if any, are needed, go on the second shell of oxygen, and how many electrons, if any, are needed, go on the third shell. All right, so whether or not you want to you can just figure it out in your head and do it that way, or if you want to do like what Crystal is doing and draw it out on a piece of paper, you're more than welcome to do either way, as long as that helps you figure out not just the proton, neutron, and electron number, but also how many electrons go on each shell of oxygen. If you don't think that you'll need any electrons on that shell, then you can just answer 0 or none. But if there are electrons on that shell, I want you to tell me how many. And again, it's not how many total electrons can fit on the second shell. I want to know specifically for oxygen, how many electrons go on the second shell of oxygen and how many electrons, if you need any, go on the third shell of oxygen. So that is the assignment for today. Again, since you guys came to the Zoom call today, you don't have to do this right away to get your attendance credit. You can wait and do it later on in the week or over the weekend or tomorrow if you want to use it for your attendance credit tomorrow. But if you do it today, then tomorrow's assignment has to do with the metals and metalloids section that we went over kind of at the end of the notes today. So this is Thursday's assignment, which will be posted at 12:01 a.m. tomorrow morning. And essentially, all you have to do with this one is put little check marks or little boxes. Which one of these descriptions fit these three categories: metal, metalloid, or non-metal? The biggest thing to keep in mind for this one is there may be more than one type of substance that matches the description. So maybe more than one of these is normally shiny. Maybe more than one of these are solids at room temperature, right? So if you think that it's 2 of them, you can put checkboxes in 2 of the categories. Otherwise, if you think that this just describes one type of substance, then you just put the checkbox in the category that fits that substance. This is what the Google form looks like. The Google Doc is same setup, just a little bit differently. Essentially, instead of checking a box, all you have to do is write down yes or no in each one of these boxes. So each line should look something like yes, yes, no, or no, no, yes, or no, yes, no, something kind of like that. So whichever one of those ways works best for you, that will be the assignment that gets posted tomorrow. Today's assignment is the one with oxygen, figuring out protons, neutrons, electrons, and their shells. And then finally, if you ever want to go back and look at the notes that we talked about today, it is under the electron shells section of the 916 Wednesday notes. And once we finish up today, I'll post the video of our Zoom call in the electron shells Zoom meeting recording section.
Mr. Stanley, you said you're going to post the other ones tomorrow, the homework, because I guess I jumped to the oxygen one. I don't.
Yeah, so
Okay.
The oxygen one is the one that got posted today.
And then the other one will be posted tomorrow? Okay, so I'll just wait till tomorrow to start the other. Okay, thanks.
Exactly. And Carmen, you had a question just now about always the protons and electrons being equal. In terms of this class, yes, that is true. So in more complicated chemistry, there are a lot of cases where the protons and electrons won't balance out, and some elements will have a positive charge or some elements will have a negative charge. But for this class, for Michael Stanley's IPC class, the protons and electrons will always be balanced. We'll always consider the atoms we're looking at as neutral, having equal positives and negatives. All right, good final question. All righty. Anybody have any final questions, thoughts, wonderings about any of the stuff that we've talked about so far today? Alrighty, I'm going.